In this video, we shall look at the Bohr model and use it to derive the energy levels of hydrogen atom. So first, we shall look at the postulates of Bohr model. So in the case of a hydrogen atom, you have a proton in the middle and an electron outside. So the first postulate is the electron moves in circular orbits about the proton. Like that. Of course, there can be many orbits. 3 of them are shown here. So Bohr postulated that this electron can only revolve in circular stable orbits, such as this orbit, that orbit, that orbit, and so on. It cannot occupy any region in between these orbits, such as those regions, that regions, and so on. One can associate definite energy with each orbit. For example, let's say the energy of the innermost orbit is E1, the second orbit, its energy is E2, E3, and so on. So when the electron is in the second orbit, it has an energy of E2. When it's in the innermost orbit, its energy is E1, and so on. And this electron can revolve around this orbit without emitting any radiation or energy. However, when the electron makes a transition from one of these stable orbits to another, for example, let's say from the second orbit to the first orbit, like that, then the atom will radiate energy, and the amount of energy radiated is E2 minus E1, namely the energy in the initial state minus the energy in the final state. The frequency of the radiation, let's call the frequency nu, is related to the change in the atom's energy, E2 minus E1, in the following manner. E2 minus E1 equals a constant times the frequency of the radiation. This H is what we call the Planck's constant. And its value is about 6.626 times 10 to the power minus 34 joule second. Another important postulate is that the angular momentum is quantized. Namely, the angular momentum of the electron must be an integral multiple of a constant h over 2 pi. So this is the same h that appears over there. So coming back to this model, if the speed of the electron there is, let's say, v, the radius of that orbit is r, then the angular momentum of the electron is the mass of the electron times that radius times that speed. And that equals n times h over 2 pi. Using these two results, now we can derive the energy levels of hydrogen atom. So let's do just that. Again, let's look at the schematic diagram of an hydrogen atom. The radius is r. The electron is moving like that with a tangential or orbital speed of v. The charge of proton is q. The charge of electron is q. So the electron is moving in that circular orbit under the influence of the Coulombic force of attraction from the proton. And that force will head in that direction towards the center of the orbit. So let's call this force F. F, or the Coulombic force, is the one that produces the centripetal acceleration. So the expression for the Coulomb force is simple, K times the product of the two charges, Q times Q, so Q squared, over the distance squared. And since it is a circular motion, there must be a centripetal force, with the centripetal acceleration AC equals v squared over r. So the Coulombic attraction indeed provides the centripetal force, which is the mass of the electron times v squared over r. This is the centripetal force on the electron. So by examining these two terms, you see that r goes away, and we get an important result for mv squared equals to k q squared over r. So let's save this equation here. Now let's look at the total energy of this electron, which is just the sum of kinetic energy and potential energy. The kinetic energy, as we know, is half times the mass of the electron times the square of its orbital speed. The potential energy of the electron is due to that interaction between electron and the proton, and it's given by minus k, the product of the two charges, q times q, so q squared, over the separation distance, which is r. So k plus u becomes half mv squared minus k q squared over r. Since we already find from this expression mv squared is all that, substituting that information in here, it becomes half kq squared over r minus kq squared over r. So the energy is half minus half kq squared over r. We will record that result here for future use. Note that this is one of the possible orbits. So let's assume this is the nth orbit. That means this is the energy of the nth orbit, and we can label the radius of the orbit with subscript n and the orbital speed with subscript n as well, like that, where n can be 1, 2, 3, and so on and so forth. To these two expressions, let's include the quantization of angular momentum, which is m times r sub n v sub n equals n h over 2 pi. This h over 2 pi can be written as h bar like that. So the quantization of angular momentum of that electron can be written as n times h bar. The next step is to solve for r sub n and v sub n using these two equations. From that equation, we know that v sub n equals n h bar over m times r sub n. Substituting this result in that equation, we can obtain a formula for r sub n, which is n squared h bar squared over k q squared times the mass of the electron. And finally, using this expression inside En, we obtain the result for the energy level, which turns out to be minus k squared power 4 of the electronic charge times the mass of the electron over 2 times h bar squared n squared, which is the equation that we have been looking for. This expression also represents the energy levels of the hydrogen atom. Using the known values of these constants, K is the constant that appears in Coulomb's law, so 9 times 10 to the power 9 in SI unit. Q is the electronic charge, about 1.602 times 10 to the power minus 19 Coulomb. M is the mass of the electron, which is about 9.11 times 10 to the power minus 31 kg. And H is the Planck constant, which is 6.626 times 10 to the power minus 34 joule seconds. Substituting all these numbers in here, we get E sub n as minus 2.185 times 10 to the power minus 18 over n squared in the unit of joules. Again, keep in mind, H bar is h over 2 pi. One can also write this in a more conventional way in a unit of electron volts, and to do that you have to divide this constant by electronic charge. So it becomes minus 2.185 times 10 to the power minus 18 over 1.602 times 10 to the power minus 19 n squared. And the unit is, of course, electron volt, because 1 electron volt is 1.602 times 10 to the power minus 19 joules, which will give you an expression as follows. Energy level is minus 13.6 over n squared in the unit of electron volts. So for example, if this particular electron is in n equals to 1 orbit, then its energy is quite simply minus 13.6 electron volt. If this electron is in n equals to 2 orbit, then its energy there is minus 3.4 electron volt, and so on and so forth. So these two expressions represent energy levels of hydrogen atom, predicted by the Bohr model. Let's do the following problem. What is the energy emitted in the transition n equals to 3 to n equals to 1 of the hydrogen atom? Namely, when the electron makes the transition from that orbit to that orbit, what is the energy emitted? Find also the wavelength of the corresponding photon emitted, or quite simply the wavelength of the radiation. We have found the energy level is given by minus 13.6 over n squared in the unit of electron volt. So the initial state of the electron is E3, and that's given by minus 13.6 over 9 electron volt. And the final state is represented by n equals to 1 orbit, and the energy there is minus 13.6 electron volt. So the energy emitted is the initial energy, E3, minus the final energy, E1. So that's going to be minus 13.6 over 9 minus 13.6 is plus 13.6. This is in the unit of electron volt, and the answer is about 12.1 electron volt. Or in the unit of joules, it is 1.94 times 10 to the power minus 18 joules. Remember, 1 electron volt is 1.602 times 10 to the power minus 19 joules. So that is the conversion. Now let's do the second part, the wavelength of the radiation. We know that the energy emitted equals the Planck constant times the frequency of the radiation. Now we know the frequency of a wave times the wavelength equals the speed of that radiation, which in this case is the speed of light. So substituting the numbers, we should do the calculation in joules. So energy is 1.94 times 10 to the power minus 18 joules. Planck constant is 6.626 times 10 to the power minus 34. The frequency in terms of wavelength is given by the speed of light c over the wavelength. Keep in mind the speed of light in vacuum is about 3 times 10 to the power 8 meter per second. So substituting this number in here, we can solve for the wavelength. And when you do the calculation, you get the wavelength to be 1.02 times 10 to the power minus 7 meter. Or in nanometer, 102 nanometers. That solves the problem. Thank you for watching.